All right, get ready for this, because today we're diving headfirst into the world of particle physics, trying to uncover the secrets of the Higgs boson, and maybe even, just maybe, uh, a hidden sector.
Oh, a hidden sector. Now that's a story for another time.
Well, today's the day, because someone sent us a fascinating paper, Emergence of the Electroweak Scale through the Higgs portal, and it sounds like we're in for a wild ride.
Oh, this paper. It really goes deep, doesn't it? Let's see if we can break it down.
Exactly. But before we get ahead of ourselves, we have to start with the Higgs boson itself, which is, well, I mean, it's only the particle responsible for giving mass to, well, everything else in the universe.
It's like the VIP of the universe, you know? Everyone knows the name, everyone wants to be seen with it.
Okay, I like that. So the Higgs boson was discovered back in 2012. It was a huge deal for physics because it confirmed a major prediction of the standard model of particle physics, which is our best theory so far for explaining the fundamental building blocks of, well, everything.
Right. It was a big win for the standard model, for sure. For a while there, we thought we had it all figured out.
But then,
But then we took a closer look at the Higgs, you see, and we realized something was a little off.
off how?
Well, that's the thing. The Higgs, it should be much, much heavier than what we've actually observed. This is what we call the naturalness problem.
So it's like we found the missing piece of the puzzle, but it doesn't quite fit.
Exactly. It's like, I don't know, trying to fit a square peg in a round hole. It just doesn't quite work the way we expect it to. And that right there, that unexpected lightness, it's a major head scratcher, you know? And it might just suggest that there's something else out there, something beyond the standard model influencing the Higgs mass.
Okay, so is that where this hidden sector idea comes in? Is this paper suggesting there's a whole other world of particles and forces out there secretly pulling the strings?
That's one of the possibilities, yeah. But to understand that, we have to talk about another fascinating concept, the Coleman-Weinberg mechanism.
Let's hear it. What makes this mechanism so special?
Well, it offers a different perspective on how particles get their mass. Instead of it all coming from the Higgs boson, the Coleman-Weinberg mechanism suggests that, get this, particles could actually acquire mass through their interactions with the quantum vacuum itself.
Wait, hold on. The quantum vacuum. Isn't a vacuum supposed to be empty?
That's what you'd think, right? But here's where things get really wild. Even in a perfect vacuum, there's this constant, like a bubbling, a sea of virtual particles popping in and out of existence. It's like a, what do they call it? A quantum foam.
So you're saying that this foam, this quantum craziness, could actually be giving particles mass?
That's the idea. It's all based on a concept called dimensional transmutation, which basically means some quantities in physics might seem simple at first, but they actually have hidden depths, like hidden dimensions, that affect the universe in ways we're only just starting to understand.
Okay, so like there's more to these quantities than meets the eye. They're not just numbers on a chalkboard. They have like a secret life influencing the universe.
Exactly. Imagine you're looking at a flat painting and suddenly, bam, it pops out, revealing all these hidden layers and dimensions you never knew were there. That's dimensional transmutation.
This is already blowing my mind. But how does this Coleman-Weinberg mechanism, with its hidden dimensions in quantum foam, how does it all connect back to the surprisingly light Higgs boson?
Ah, now that is the million-dollar question. And it's what makes this paper so intriguing. You see, when physicists first applied the Coleman-Weinberg mechanism to the Higgs, it predicted a mass even lower than what we actually observed.
So not a perfect solution then.
Not quite. It's like, imagine we replaced a bowling ball with a ping pong ball. Not exactly what we were hoping for. But, and here's where things get really interesting, this paper suggests that a hidden sector could be the missing piece of the puzzle.
Okay, hold on. A hidden sector, you have to break this one down for me. Are we talking about like a parallel universe here or something?
Well, it's not exactly a parallel universe, not in the, science fiction sense anyway, but it is a pretty mind-blowing idea. Imagine this, okay? Our universe, with all its particles and forces, it's like a giant, vibrant tapestry.
Okay, I'm with you so far.
Now, picture this tapestry being woven on an even bigger, like cosmic loom, right? And on this loom, there are other tapestries being woven alongside ours, each one a different sector with its own unique set of particles and forces.
So different universes, each with their own unique properties.
Exactly. And these sectors, they might not interact with ours in any obvious way. They could even have different laws of physics altogether. But And here's the kicker. This paper suggests that there could be like subtle connections between them, like threads interlacing between the tapestries.
And these threads, are those the portals you mentioned earlier?
You got it. These portals would be like points of contact where particles from different sectors could, interact, even if it's just a little bit.
So even though these sectors are mostly separate, they're not totally isolated.
Exactly. It's like, imagine two musicians playing in separate rooms, right? You can't see them, but you can hear the music kind of blending together through the walls. And in the same way, a hidden Higgs particle living in this hidden sector could be subtly influencing the mass of our very own Higgs boson.
This is wild. But if this hidden Higgs is doing its thing in a whole other sector, how on earth could we ever find it? I mean, it's not like we could just point a telescope at it.
You're right. Directly observing a particle from a hidden sector is, well, it's beyond our current capabilities. But, and this is the beauty of science, we don't always need to see something directly to know it's there. We just have to look for its fingerprints, its influence on the things we can observe.
Okay, now you've got me intrigued. What kind of fingerprints would a hidden Higgs leave behind?
Well, one of the best ways to look for it is to study how our own Higgs boson decays. You see, the Higgs boson is extremely unstable. It exists for a tiny fraction of a second before decaying into other particles. And the way it decays, the specific particles it breaks down into, that can tell us a lot about its properties and what it interacts with.
So the hidden Higgs, even though we can't see it directly, could be messing with how our Higgs decays.
That's the idea. It's like leaving a hidden message.
So by carefully analyzing all the data from these decays, we might find some weird stuff, some things that don't quite fit with what we expect from the standard model alone. And those anomalies, those could point to a hidden Higgs.
Exactly. Like finding a needle in a haystack, it's all about precision. Looking for those tiny deviations, those whispers in the data that might just lead us to something revolutionary.
Okay, so how do we even begin to look for these whispers? Are current particle accelerators up to the job?
Well, the Large Hadron Collider, or LHC, has been amazing for advancing our understanding of particle physics. But to really dig into this hidden sector, we might need something even more powerful. Imagine a collider that can smash particles together at energies we can only dream of right now.
Okay, so much, much bigger atom smasher. What would that even look like?
It'd be massive for sure, but it would be like having a giant microscope, allowing us to see the universe on a scale we've never seen before.
So we need new technology, but in the meantime, what can we do?
We're not at a standstill. We can still do a lot with the data we have, and of course, theoretical models play a huge role. This paper, for example, it lays out some pretty innovative strategies for searching for these hidden Higgs signatures and improving our detection methods.
Okay, so it's a two-pronged approach. We're pushing the boundaries of technology and theory at the same time. I have to say, the more I learn about this hidden sector, the more fascinating it gets. But I gotta ask, on a more fundamental level, why does all this even matter? Why should we care about a hidden Higgs, a whole sector of the universe we might never even be able to interact with?
That's a great question, and I think the answer gets at the heart of what science is all about. The search for this hidden Higgs, this hidden sector, it's not just about finding a new particle, it's about pushing the boundaries of what we know, of understanding our universe on the deepest level possible.
So it's about the big picture, the quest to unravel the ultimate mysteries of the cosmos.
Exactly. For centuries, humans have looked up at the stars and wondered, are we alone? What else is out there? And this idea, this possibility of a hidden sector subtly influencing our own, it adds a whole new layer of mystery to the universe.
It's like realizing the universe is even bigger and stranger than we ever imagined.
Precisely. And the coolest part is we're only just beginning to scratch the surface. This paper, it suggests that this hidden sector might not only be influencing the Higgs boson, but it might have also played a key role in shaping the entire universe as we know it.
Wait, really? You're saying this hidden sector could be responsible for the universe as we see it today?
That's what this paper suggests. It has to do with the very early universe, right after the Big Bang. They're proposing that back then, the universe was in a state of, get this, scale invariance.
Scale invariance. Now, that's a new one on me.
It's a bit of a head-scratcher, but basically it means that in those first moments, the universe had no preferred scale. There was no difference between big and small, heavy or light. It was like a cosmic soup where size was totally relative.
So you're saying that in the very beginning, the universe was just this uniform blob of stuff, no stars, no galaxies, nothing.
That's the idea. It's wild, right? But then the question becomes, how did we go from that state of perfect symmetry, that scale invariance, to the universe we see today with all its vast structures and
It's
complexities?
like, what happened to break the mold?
Exactly. And here's where this paper takes us on another wild ride. They suggest that the hidden sector, through its interactions with our universe, might have actually caused this primordial scale invariance to break.
Okay, hold on. You're saying that this hidden sector, which we can barely even detect, might have been the driving force behind the formation of, well, everything.
It's a pretty bold claim, right? They're proposing that the interaction between the hidden sector and our own could have triggered a cascade of events that led to the emergence of mass, gravity, and ultimately the universe as we know it.
This is getting pretty deep, even for the deep dive.
You can say that again, but that's what I love about this paper. It connects these big, mind-boggling ideas like the origin of the universe to the tiniest particles we know of.
It's amazing to think that something as, like, fundamental as mass, something we experience every day, could have come from such a weird, abstract idea as a scale invariant universe.
Yeah, it really makes you question what we think we know about, well, reality, doesn't it?
Absolutely. And it makes you wonder, if the universe started in this perfect state, this scale invariance, what happened? What caused it to change, to become the universe we see today?
That's the million-dollar question, isn't it? It's like trying to figure out how a firework works by just looking at the sparkles after it explodes. We're still searching for that initial spark.
So we're looking for those first tiny changes that eventually led to, well, stars, galaxies, planets, everything.
Exactly. And this paper, even though it doesn't have all the answers, it gives us some pretty interesting clues. They're suggesting that this hidden sector interacting with our universe might have been the thing that broke that initial symmetry, got the ball rolling, so to speak.
It's like the whole universe we see, all of it, is just a result of this dance between what we can see and what we can't.
That's a great way to put it. It really captures the essence of this paper. There's so much more to the universe than meets the eye.
So where do we go from here? What's next in this search for this hidden sector and its role in, well, everything?
Well, as we talked about earlier, having more powerful particle accelerators is crucial. We need those to really explore this hidden world.
Bigger, better atom smashers.
Exactly. But it's not just about the technology, it's also about the theory. We need to keep refining our models, keep coming up with new ways to look at the data.
So it's a team effort, experimentalists and theorists working together.
Absolutely. It's really inspiring, this drive to understand the universe, this human curiosity. Who knows what we might find if we keep digging?
I have a feeling we're just getting started. Well, that was quite a journey, wasn't it? We went from this tiny particle, the Higgs boson, to this mind-blowing idea of a hidden sector, a whole other world, influencing our own, potentially even responsible for, well, the universe as we know it. If you want to learn more about this, be sure to check out the show notes. We'll have links to the research paper and other resources. And until next time, keep those questions coming and keep exploring the universe because, well, you never know what you might find.